So moving on to part 3, we're now going to start using the forces that we did in the last couple videos and drawing some free body diagrams on our own and labeling the forces. So you have a worksheet on page 21 that has a bunch of free body diagrams. I'm going to walk through these one by one, and you're going to label the forces. And please try to be very consistent about labeling them using the abbreviations that I indicated in the other page so that you're being very consistent. This allows for consistency across students and across classes. So the first one is a physics book rests upon a level table. So if we think about what forces might be acting on him, and we kind of go through the whole checklist, well, there's definitely gravity, and gravity is always going to pull something down. So we should have a downward arrow labeled F grav. But there's also going to be a normal force because the book is sitting on the table and the table is supporting that. So that's our F norm, which is going to be pointing up. So you should have something like this. Because the object is at rest, it's going to have balanced forces. So we should already kind of recognize that these two forces are going to be equal in length. The next one has a skydiver is falling and has reached a terminal velocity. So you don't know this yet, but a terminal velocity is a constant velocity. So it means that it's now traveling through the air at a constant rate. So in this case, we're still going to have gravity acting on it. There is not going to be a normal force or an applied force or a friction force. However, there is going to be a air resistance force because this thing is traveling through the air. There is no tension force. So you should end up with something that looks like this. So F air is up and F gravity is down, and they should be equal in length because it has reached a constant speed. The next one is a large crate is being pushed leftward at a constant velocity. So if it's being pushed, it's most likely being on the floor or on some sort of surface. So we have an F gravity going down always, and then we have a normal force going up, and there's probably being balanced because it doesn't say that it's like levitating. Moving leftward, it's being pushed leftward, which means that it's being pushed with an applied force off in the leftward direction. And if there is, it's moving across a surface, there's going to be a friction opposing it because it is moving. So you should end up with something like this. So you'll have here a gravity and normal that are equal and opposite, and an applied going to the left and a friction going to the right. So let's move on to the next line. So the next line has a sledder has reached the bottom of a hill and is coasting rightward while slowing down. So if it's coasting rightward, coasting actually indicates a constant velocity, but there's nothing pushing on it. So it reaches the bottom of the hill, it's got a gravity force, it's got a normal force, and that's all that it's got. So there's nothing pushing on it. There's nothing else holding it back at this point. So E, a ball is moving towards its peak, ignore air resistance. So if you have a ball moving upwards through the air and it says to ignore air resistance, the only thing you have is gravity acting downward on this one. Then F, an air track glider moves rightward at a constant speed. So in this case, we've got a gravity force acting down. And instead of having a normal force, we have an air force. It's different than the air resistance, but this would be like on an air hockey board. So instead of having the pucks resting on the platform, you actually have them just pushed up a little bit by the air that's running on there, and that's why they're very, very low in friction. So you're going to have an upward force here to be due to air as opposed to a normal force. So now letter G, the brakes are applied to a rightward moving car as it skids to a stop. So in this case, we still have gravity, still riding on the road, so it has a normal, and we have friction. So the car is moving to the right and friction opposes motion, so it's going to be moving. The friction is going to be going to the left. H, a spider is slowly descending a thin silk thread at a constant speed. So we have a gravity force acting downwards, and since there's a thread pulling it upwards or helping hold it up, that's going to be our tension force. So in this case, we have tension upward and gravity downward. And since it's at a constant speed, they're going to be equal and opposite. I, a projectile is moving upwards and rightwards towards the peak of its trajectory. So in this case, we have F, gravity acting downwards. And there's a little subtlety for projectiles. Projectiles are so small that we neglect air resistance. Remember when I was talking about air resistance, we talked about things moving at high speeds and having large surface areas. Well, projectiles, which are typically considered things like little bullets, they are very small. They don't have a lot of air resistance for these types of problems. So you would not necessarily know that until doing this problem. But now from now on, when you see a projectile, you should recognize we're going to be ignoring air resistance. Letter J, an elevator is rising at a constant velocity. It is not touching the elevator shaft. So in this case, we've got gravity acting downwards, and an elevator is typically pulled up by a rope or some kind of cable. And so upwards force is going to be a tension force. For the next one, an upward rising elevator is slowing down. It is not touching the elevator shaft. So again, we're going to have gravity and we're going to have a tension force. But you notice the difference between these two. The one says it's constant velocity so that they're actually equal. These two forces are equal. In this one, the elevator is slowing down, which means we need a net force opposing motion. So that would be our net force would be going down. So they've drawn the tension force to be smaller than the gravity force here. And then in L, a force is applied to accelerate a crate across a rough horizontal surface. Now, they didn't give us a direction, so I'm going to assume right because right is positive, and that's what we just tend to like working with positive. So we're going to have it an applied force to the right, a friction force to the left, gravity down, and normal up. And since we want it balanced in the up and down, our normals and gravities are going to be equal. And if it's accelerating, kind of assuming that it's kind of speeding up, so we're going to have a larger force going to the right with our applied and a smaller force to the left going with friction. So as we go through this, I've got some notes here. This F applied and F friction here is, they were switched on the original answer key, so I wrote in my own thing. Comment here about friction in air. It would be true if the object was not going at a constant velocity, but since it is going at a constant velocity, you really are going to neglect the friction and the air resistance. So cleaning it up, this is what the answer key looks like. So now after doing the 12 of these, sometimes students are ready to go ahead and move on to the MOP app, which goes over this. Sometimes students are saying, oh, I really need some more practice. So I have provided a second practice sheet for you. It's in your packet. It is page 22. It's going to be very similar. But I do encourage you to take a look at this, and I will have the answer key posted on Google Classroom. So once you're done with this, you can just go ahead and take a look at Google Classroom. If you have any questions, just let me know. But your MOP app is going to be NL5. And again, you are not required to do this page and turn it in. I suggest it might be helpful for some of you, especially if you're not too confident, and it shouldn't take you too long to do it. But you are required to turn in page 21 and the MOP app NL5. And once you're done with that, you can go ahead and take the assessment.